Could we use the sun as a gigantic telescope? What if the key to unlocking the deepest secrets of the universe is right in front of us, hidden in the heart of our solar system? Imagine the power of seeing distant exoplanets and galaxies with a resolution 1,000,000 times greater than what we have today. What would we discover? In our quest to understand the universe, humanity has built some truly incredible tools. From the Hubble Space Telescope to the more recent James Webb Space Telescope, JWST, these observatories have allowed us to peer back in time, capturing light from the earliest moments of the universe. They've revealed breathtaking images of distant galaxies, nebulae, and even the atmospheres of exoplanets. Each new telescope brings us closer to answering the age-old question, what's out there? But what if there was an even more powerful tool already at our disposal, and we didn't have to build it? What if the ultimate telescope was not something constructed in a lab, but rather, something that has been burning in the center of our solar system for billions of years, the sun itself? This idea isn't as far-fetched as it might sound. In fact, there's a well-known phenomenon in astronomy called gravitational lensing, where massive objects like stars or galaxies bend the fabric of space-time around them, causing light to curve. Essentially, these objects act as cosmic magnifying glasses, allowing us to see distant objects that would otherwise be invisible or too faint to detect. Scientists have used this technique before to study the farthest reaches of space. For instance, when light from a distant galaxy passes by a cluster of galaxies, the cluster's gravity magnifies and brightens the distant image, enabling astronomers to study galaxies billions of light years away. But what if we took this concept one step further? What if we used the sun as our gravitational lens? The idea is simple in theory. The sun's massive gravitational field warps spacetime around it, bending the light that grazes its surface. This light doesn't continue in a straight line, but instead, converges at a distant focal point, much like a magnifying glass focusing sunlight. At this focal point, astronomers could place a spacecraft to capture this focused light, creating a telescope with a mirror effectively as wide as the sun itself. The result? A telescope with a resolution so powerful that it would make even the most advanced observatories we have today look primitive in comparison. This concept, known as the solar gravitational lens, could unlock unprecedented views of the universe. Imagine seeing the surface of a distant exoplanet in exquisite detail, being able to map continents, oceans, and even weather patterns from light years away. It sounds like science fiction, but the physics behind it is very real. In this video, we'll explore how this works, the challenges involved, and what this super telescope could mean for the future of astronomy. Over the years, humanity has made incredible strides in building telescopes that have transformed our understanding of the cosmos. Take, for example, the James Webb Space Telescope, JWST. Launched in 2021, the JWST has already given us astonishing images, capturing the birth of stars, detailed views of galaxies, and even the chemical compositions of distant planets' atmospheres. Its technology allows us to see deeper into space than ever before, revealing parts of the universe that were once invisible. With a mirror spanning 6.5 meters and highly sensitive infrared instruments, the JWST is currently one of the most powerful tools for exploring space. And then there's the Event Horizon Telescope, EHT. This groundbreaking telescope isn't just one instrument, it's a global network of radio telescopes synchronized to work as one. In 2019, it gave us the first ever image of a black hole's event horizon, a truly historic moment in astronomy. By combining the power of telescopes around the world, the EHT achieved a staggering resolution of 20 microarcseconds, enough to spot an orange on the surface of the moon. These telescopes represent the pinnacle of human engineering, the result of decades of innovation and billions of dollars in investment. They're capable of looking back in time, showing us what the universe looked like billions of years ago. But even with all their power and precision, there are limits. For one, the resolution of these telescopes is constrained by the size of their mirrors. No matter how large we make them, there's a physical boundary to how much light they can collect and how detailed the images they can produce. The Event Horizon Telescope, for example, relies on a network of telescopes spread across the globe, a feat of coordination and technology, but still, it required a combination of multiple observations over time to produce its iconic image of a black hole. This brings us to the solar gravitational lens. Unlike any traditional telescope, it doesn't rely on a mirror or a lens. Instead, it leverages the sheer mass of the Sun to bend light and focus it at a point far beyond the orbit of Pluto. In essence, the Sun itself becomes a natural telescope, with a lens the size of the Sun's entire circumference, a lens far beyond anything we could ever build with current technology. The power of this solar lens is hard to comprehend. It could achieve an angular resolution of 10 to the power of -10 arcseconds, making it about 1,000,000 times more powerful than the Event Horizon telescope. To put this in perspective, if we aimed this telescope at Proxima b, the closest known exoplanet, we could see details on its surface with a resolution of just 1 kilometer. That's not just detecting an exoplanet, that's seeing individual features on its surface, like land masses, oceans, or even weather patterns. Compared to what the JWST or EHT can currently achieve, this level of detail is unimaginable. While our most advanced telescopes today can barely make out distant exoplanets as tiny dots of light, the solar gravitational lens could deliver high-definition images of entire planetary landscapes. But it doesn't stop there. This telescope could allow us to observe objects across vast distances in space, making it possible to study the structure of far-off galaxies, distant black holes, and perhaps even the edges of the observable universe. For astronomers, this would be nothing short of revolutionary, as it would give us access to detailed data and images far beyond what current technology can provide. The solar gravitational lens represents a quantum leap forward, far surpassing anything that modern telescopes can offer. However, before we get too excited, we need to understand the challenges that come with using the Sun as a telescope, challenges that require advanced technology and a bold new vision of space exploration. Let's dive into those next. Now that we understand the potential power of the solar gravitational lens, let's explore how it actually works. At its core, this concept relies on Einstein's theory of general relativity, which tells us that massive objects like the Sun bend the fabric of space-time. This bending of space causes light to curve around the Sun rather than traveling in a straight line. Essentially, the Sun acts as a cosmic magnifying glass, bending and focusing light at a specific point far from the Sun. This is known as the focal point. For the solar gravitational lens, the focal point is an astonishing 542 astronomical units, AU, away from the Sun. To give that distance some perspective, 1 AU is the distance between the Earth and the Sun, so 542 Australian dollars is about 11 times the distance of Pluto from the Sun. It's also more than 3 times farther than the distance reached by Voyager 1, the most distant spacecraft we've ever launched. At this focal point, a spacecraft could capture light that has grazed the Sun and been bent into focus. The result? The light from distant objects, like exoplanets or galaxies, would be magnified with incredible resolution, as if we were using a telescope with a mirror the size of the entire Sun. However, the process isn't as simple as placing a telescope at that point. The image created by the solar gravitational lens would be spread out over tens of kilometers, meaning that a spacecraft would need to scan the entire area to build a complete picture. This would require sophisticated instruments capable of slowly piecing together the light into a detailed mosaic of the observed object. Moreover, the spacecraft would need to travel beyond the farthest reaches of our solar system, where it would have to operate autonomously, manage limited fuel, and communicate over vast distances. To make this possible, scientists have proposed sending lightweight, solar sail-powered probes or CubeSats that could accelerate to these incredible distances without requiring massive amounts of fuel. While the concept seems far-fetched, the physics behind it is solid. The real challenge lies in the engineering required to deploy a spacecraft at such extreme distances. But if we can overcome these hurdles, the rewards, unimaginable views of the universe, could be beyond anything we've ever dreamed of. Although the idea of using the Sun as a gravitational lens is scientifically sound, the journey to make it a reality presents some significant technological challenges. First and foremost is the sheer distance involved. To harness the solar gravitational lens, a spacecraft would need to travel 542 Australian dollars from the Sun, a distance humanity has never reached before. The most distant spacecraft to date, Voyager 1, launched in 1977, has only traveled about 160 Australian dollars over more than 40 years. So, how do we get 3 times farther than that? This challenge of distance introduces 2 critical issues: time and fuel. A traditional spacecraft using chemical rockets would take decades or even centuries to reach the focal point. We'd need a more efficient propulsion system to significantly cut down that travel time. This is where the idea of solar sails comes in. Solar sails are a cutting-edge propulsion method that uses light from the sun to push a spacecraft forward, much like wind moves a sailboat on the ocean. These sails could accelerate small, lightweight spacecraft, like CubeSats, to speeds that would allow them to reach the solar lens in just a few decades. Once the spacecraft reaches its destination, it faces another challenge: maneuvering and scanning. The image produced by the solar gravitational lens wouldn't be concentrated in one spot. Instead, it would be spread across an area tens of kilometers wide, requiring the spacecraft to move methodically and capture different segments of the image to create a detailed composite. This is no small feat. It demands precise navigation and coordination between spacecraft, all while dealing with the immense distance and limited energy sources. One possible solution is to deploy a fleet of small, autonomous CubeSats. These mini-satellites, propelled by solar sails, could work together, each capturing different parts of the image and sending data back to Earth. Their small size would make them easier to accelerate to the necessary speeds, and working in unison, they could build a detailed mosaic of the target object, be it a distant exoplanet or a far-off galaxy. Another technological hurdle is communication. At such distances, the time it takes for a signal to travel between Earth and the spacecraft would be hours, making real-time control impossible. The spacecraft would need to operate autonomously, capable of making decisions and performing scans without human intervention. Additionally, transmitting the massive amounts of data gathered by the solar gravitational lens back to Earth would require advanced communications technology to handle the vast distances and data loads involved. Despite these challenges, the potential payoff is enormous. With this technology, we could capture images of distant exoplanets with resolutions so fine that we could distinguish landforms, oceans, and perhaps even signs of life. No current or planned telescope, even the successors to the James Webb Space Telescope, can come close to this level of detail. And while these hurdles may seem insurmountable now, the rapid pace of space technology gives us hope. Just a few decades ago, landing on Mars or sending a probe to the edge of the solar system seemed impossible, but today these are realities. By developing lightweight, efficient spacecraft and harnessing innovative propulsion methods, the dream of a solar gravitational lens telescope could be within reach, perhaps within our lifetime. In the next section, we'll explore what this groundbreaking technology could reveal about the universe, and how it could revolutionize our understanding of distant worlds and cosmic phenomena. The possibilities unlocked by a solar gravitational lens are staggering. Imagine detailed images of exoplanets, revealing mountains, oceans, or even signs of life. We could map the surfaces of distant worlds, study the atmospheres of planets light years away, and even observe the earliest galaxies in unprecedented detail. This super telescope would be our most powerful tool to uncover the mysteries of the universe. But these discoveries are only possible if we push the boundaries of space exploration. The future of astronomy lies not just in building bigger telescopes but in harnessing the universe itself. Are we ready to take the leap?